once again in the video lecture of Communication Engineering, lecture 16. In today's video lecture, we are going to discuss about the pulse code modulation technique. We know that a pulse code modulation technique is a kind of digital pulse modulation technique. Pulse code modulation, that is also called as PCM, is a common method of converting analog signal into digital signals. The noise performance of digital system is much better than that of an analog system. That is why we used to prefer digital communication techniques over analog communication techniques. And PCM is a kind of digital modulation technique. PCM system allow the representation of a continuous time signal as a sequence of binary codes that is in the form of zeros and ones. The pulse code modulation process will be performed with the help of three simple steps, that is sampling, quantization and then coding. Actually, pulse code modulation is a kind of analog to digital conversion technique. To convert analog signal into a digital signal, we have to perform these three steps together, that is sampling, quantization and encoding or encoding. So the output of the output after the coding, after performing these three steps, will be in the form of digital signal. So let us check how we can convert analog signal into digital signal with the help of pulse code modulation system. This entire setup that includes sampling, quantization and coding, this complete process is called as pulse code modulation. In pulse code modulation, we don't use any high frequency carrier signal that will carry the information. Rather, PCM is a kind of digital modulation technique where the input signal will be a continuous time analog signal and the output will be in the form of digital signal. Okay. So, the very first step in PCM process is the sampling. We have already discussed about the sampling. What is sampling? Sampling is the process of converting a continuous time signal into a discrete time signal. We used to perform the sampling of an analog signal in time axis. So, the first step is the sampling. The input to the sampler will be an analog signal, that will be a continuous time analog signal. The analog signal will be continuous in time as well as continuous in amplitude. Okay. So, when we will perform the sampling, the output of the sampler will be a discrete time signal. Now, this continuous time analog signal will be discretized in time axis. Sampling makes the signal discrete in time. The next step is the quantization. What is quantization? Quantization is the discretization of the signal in the amplitude axis. The output of the quantizer will give us discretized signal that will be discretized in magnitude axis. The output of the sampler is what? The output of the sampler is a signal which is discrete in time axis, but this signal is still continuous in amplitude axis. So, we have, if we want to convert the analog signal into digital signal, the next step is to discretize this signal in magnitude axis also. That can be done with the help of quantizer. So, quantization makes the signal discrete in amplitude axis. Then after this, we have to apply an encoder. What this encoder will do? The encoder will assign binary numbers to the quantized amplitude levels of this particular signal. So, after passing this signal from an encoder, that will assign a binary pattern to each level, we will get the final output that will be in the form of digital signal. So, when we will get this kind of representation of this continuous time analog signal, then we can say our analog signal will be converted into a digital signal. So, this entire process that includes sampling, quantization and encoding is called pulse code modulation technique. In pulse code modulation, our input will be an analog signal and our output will be a kind of digital signal, that is in the form of zeros and ones. Let us check the PCM system, that includes the PCM transmitter, transmission path, and the PCM receiver. The very first block of the PCM transmission system is a low pass filter, that is also called as anti-aliasing filter. The first step in the PCM process is to perform the sampling. Before performing the sampling, we will pass our analog information from an anti-aliasing filter to prevent any aliasing to occur. What this low pass filter will do, it will remove the unnecessary high frequency component present in the information. Then the next block in this process is the sampler. The sampler will perform the sampling of the incoming signal with the rate Fs greater than twice of Fm. That is, the sampling frequency must be greater than equals to twice of the maximum frequency component present in the master signal, so that when we want to recover the information back from its sample, there will be no aliasing. Okay. Then after this, we will have a quantizer that will discretize the incoming signal in magnitude axis. Then we will have an encoder that will provide the codes in the form of zeros and ones to each level, and finally we will have the PCM output, that is the digital output. Then this signal will travel from through the channel. The transmission path, this is the transmission path. This transmission path includes some regenerative repeaters. The transmission path includes regenerative repeaters or regenerative receivers. What these regenerative repeaters will do, these regenerative repeaters will recover the signal from the undesired noise effects. When traveling through the channel, the signal will become distorted due to the effect of noise. These regenerative repeaters at a certain distances will again regenerate the signals and help us in removing the undesired noise or the undesired distortions that will occur in the transmitted signal. Then at the receiver, we will have the regenerated signal, that is the regenerative PCM signal. It will be passed from a regeneration circuit, and then it will be passed from a decoder where the signal or the digital information will be decoded, and at last it will be passed from a reconstruction low pass filter that will again provide us the original information. So this is the entire PCM process or the PCM system. The transmitter will include sampling, quantization and encoding. Transmission path includes regenerative repeaters, and the receiver will include the regeneration circuit, decoder and the reconstruction with the help of low pass filter. Okay. Now let us discuss the process of quantization in detail. The process of sampling we have already discussed in the last video lecture. So now let us discuss what actually quantization is and how we can perform quantizations, what are the methods with the help of which we can perform the discretization of the analog signal in magnitude axis or in amplitude axis. So quantization is a process in which the continuous range of values, that is the amplitude of the signal of an analog signal, is sampled and divided into a well separated sub ranges, and a discrete unique value is assigned to each sub ranges. That means what we will do in quantization, the continuous amplitude of the analog signal will be divided in some levels. These levels we can call as sub ranges, or the levels in which we are dividing our analog signals. So the quantization is a process of sampling the continuous amplitude of the analog signal into discrete manner or into a discrete form. Quantization we can also call as a process of rounding off the sample values to the closest quantization levels. That means if at this point we have some samples and some of the sample is lying between the two anywhere between the two levels then we have to assign either the lower one or the upper one to that particular sample point. So we can also call quantization is a process of rounding of the sample value to the closest quantization level. That we will also see with the help of diagram in our next slide. So what we can say, quantization is a method of converting a continuous amplitude sample into a discrete time signal. It is a device that performs quantization. The device that is used to perform this sampling in the amplitude axis is called quantizer. The space or the gap, the levels that we are assigning to the in the amplitude axis of this of the signal, these levels or these spaces or these gaps between the two adjacent quantization level is called step size. We used to represent a step size with the help of this symbol that is called delta. Okay. So what is a step size? A step size is the space or the gap between the two adjacent quantization levels. The difference between the quantized value and the sampled value of analog signal is called quantization error. That means if our sample is lying anywhere in between the two levels or in between the gap, then we have to assign a particular value to that particular sample, that is the either the higher level or the lower level. This difference between the actual value and the assigned value is called quantization error. The quantization error we can calculate with the help of this simple mathematical relation, that is the quantized signal, the value that we have assigned to that particular sample minus input signal, that is the original value of that particular signal. Now let us discuss what is quantization with the help of this figure. So what we will do in case of sampling, if this is this blue waveform is presenting our continuous time analog signal. So what we do in sampling, we used to discretize our continuous time analog signal into a discrete time signal. That means we assign samples at regular time interval. The spacing between these samples is uniform. And if we follow this particular criteria, that is Fs greater than equals to twice of Fm, that is the Nyquist criteria, then it can be said that these samples will contain all the information about the analog signal. This is the sampling. So after performing the sampling, the signal, the analog signal will become discretized in time axis, but it is still continuous in amplitude axis. So what we will do in quantization we assign a particular level at the amplitude axis. We perform the same discretization in the amplitude axis. This is called quantization. So what quantized signal is the discrete in amplitude axis. So this is called quantization levels. The gap between the two adjacent level is called step size. So how we can calculate the step size? Step size can be calculated with the help of this simple relation, that is the maximum amplitude range of the analog signal minus minimum value of this amplitude signal divided by L, that is the quantization levels. That means in how many ranges we have divided the amplitude of this analog signal. The number of, with the help of number of levels, we the next step after the quantization is encoding. That means if we are increasing the number of levels, then we have to increase the number of bits to represent each level. So there is a relationship between the quantization level and the number of bits required to represent each level. Okay, so there is a relation, that is L equals to 2 raised to the power n, where n is the number of bits required to represent each level, or we can say n is equals to log base 2 quantization level. Okay, this leveling we can do in two ways. Either we can decide uniform gap between the two adjacent level, or we can decide non-uniform gap between the two adjacent levels. So depending on this, we can have two types of quantization. The quantization can be divided in uniform quantization and non-uniform quantization. What is uniform quantization? In case of uniform quantization, the step size we used to kept fixed and it will be equal for all the levels. In non-uniform quantization, the step size will be unequal, or the gap between the two adjacent levels can vary from one to another. So first we have uniform quantization. In uniform quantization, we can have mid-rise uniform quantizer, or we can have mid-tread uniform quantizer. What is mid-rise and what is mid-tread uniform quantizer? First of all, uniform quantization is the quantization where the levels are uniformly spaced. That means these levels are uniformly spaced. That means the gap between each level will remain similar. That is, the step size of each level will be similar. Okay. So in uniform quantization, the quantization levels are uniformly spaced such that the equal spacing between the quantization level. Uniform quantization is also called as linear quantization. So uniform quantization of mid-rise types is a kind of uniform quantizer where the origin lies in the middle of the raising part of this staircase-like structure, while the mid-tread uniform quantizer is a kind of uniform quantizer where the origin lies in the middle of the tread of this staircase-like structure. So we can either opt this kind of uniform quantizer or this kind of uniform quantizer, but the gap between the two levels will remain same throughout the quantization process. Okay. The next is non-uniform quantization. First of all, why we require non-uniform quantization? If we already have the uniform quantization, the quality of the quantizer output depends on the number of quantization levels. More the value of levels, lesser will be the quantization noise in general. However, on increasing the number of quantization levels, more will be the quantization levels, lesser will be the quantization noise. But if we'll keep on increasing the number of levels, if we'll keep on increasing the number of quantization levels, the number of bits required to represent each sample and each level will also increase. Hence, it will increase the total bandwidth requirement, bit rate, and also the cost of transmission. So what we can do, we can use non-uniform quantization. In non-uniform quantization, levels, this is representing the levels. In non-uniform quantization, the levels are non-uniformly spaced. Here we can observe the gap between the two levels is varying from one to another. This is called non-uniform quantization, or also called as non-linear quantization process. Why we require this? First, that is to deal with this problem of increasing bit rate and the bandwidth requirement. Secondly, in uniform quantization, we will have the same amount of quantization error. In some cases, uniform quantization is also not efficient. For example, in voice signals or in speech communication, generally the smaller amplitude predominate and larger amplitudes are relatively rare. So in case of speech communication or in voice communication, most of the information lie near to the zero level, we can say, and the higher amplitude signals are rarely present. So in such cases, if we'll apply the uniform quantization, the levels applied to the higher amplitude levels will be a completely wastage. So what we can do, we can opt non-uniform quantization. Where most of the information is lying, we can divide that particular part in more amount of levels, and where the information is not used or is rare, we can divide that particular part into a smaller number of levels. So, to avoid the wastage of quantized levels, we can opt non-uniform quantization for the case of speech communication or voice communication. In such cases, non-uniform quantization is more efficient. Non-uniform quantization also reduces the quantization error by optimizing the need of step size according to the information lying in a particular level. Okay. So, after this, deciding uniform quantization, whether we want to opt for uniform quantization or non-uniform quantization, that will depend upon the application. Next, we have the calculation of bandwidth for PCM signals. How much amount of bandwidth is required for the transmission of pulse code modulated signal. As we know that PCM is a non-linear process, the bandwidth of binary PCM waveform depends upon the bit rate. The bit rate we used to indicate with the help of this symbol R with B in the suffix, and the waveform pulses shape used to represent the data. So, the bit rate we can define with the help of this relation, that is RB is equals to N dot Fs, where N is the number of bits required to represent each level and Fs is the sampling rate. The Fs will be equals to we use Nyquist criteria for the sampling, that is Fs must be greater than equals to twice of Fm. So, as per the Nyquist criteria, Fs must be greater than twice of Fm. So, we can calculate the minimum bandwidth required for the transmission of PCM signal as Rb by 2, that is Nfs by 2. This is the minimum bandwidth required for the transmission of PCM signal. This is, we can say, the lower bound, and the actual or the actual bandwidth required for the transmission of PCM signal will depend on that on the type of information and the amount of information, but this is the minimum value or the minimum amount of bandwidth required for the transmission of any PCM signal. Minimum this much we require, and maximum it will depend upon the type of information. So, the bandwidth of PCM signal will become equals to Nfs by 2, or it must be greater than N into Fm. Next, we have the noise consideration in PCM system. In pulse code modulation system, we generally consider the two types of noises, that is the channel noise and the second one is the quantization noise. What is channel noise? It can be introduced anywhere between the transmitter output and the receiver input. Channel noise is always present once the system is turned on. The second is quantization noise. Quantization noise is introduced in the transmitter and is carried all the way along to the receiver output. We have seen during the process of quantization, some kind of quantization error will occur. That is the main source of this quantization noise. So, let us discuss the quantization error or noise. As we have discussed, what is quantization error or quantization noise? The difference between the input and the output signal value of a quantizer is called as quantization error. What is quantization error? The output of the quantizer and the input of quantizer, the difference between the output and the input of the quantizer. So, how we can calculate this quantization error? This quantization error will remain uniform throughout the process, or we can say the quantization error is uniformly distributed. So, the PDF of this quantization error can be described with the help of uniform probability density function, where delta is the step size. So, the probability of error or the quantization error, how we can calculate the quantization error power is the expectation value of the squared quantization error that we are representing with a small e. So, how we can calculate this? Sigma square of quantization noise is equal to the expectation of the square of this particular error, expectation of E square. So putting this value, calculating this, that is the integration from minus del by 2 to del by 2 with the help of this PDF of quantization error, integrating 1 upon delta E square with respect to del E. We will get the quantization error is equals to del square by 12. It is also represented with the help of NQ. So the quantization error or the quantization noise is equals to square of the step size divided by a factor, that is 12. The next is signal to quantization noise in case of PCM system. How we can calculate signal to quantization noise ratio? We can calculate with the help of signal power, average signal power to the quantization noise power. The quantization noise power we have calculated as del square by 12. We know how we can calculate this step size delta. It is the maximum of amplitude of the analog signal minus minimum of the amplitude of the analog signal divided by number of levels. If the amplitude we are representing with MP, then del square by 12 can be rewritten as m square p divided by 3l square. That will become 1 upon 3 m square minus of 2 m square 2 raised to the power minus of 2n, where L is equals to 2 raised to the power n, where L is the number of levels that we have seen in the case of quantization process, that how we can calculate the number of levels. It will depend how many bits we are required to represent each level, that is 2 raised to the power n. So after putting all these in this formula, we will get the quantization noise power equals to this value. The average power of the signal we can represent with the help of P average. So the quantization signal to quantization noise ratio, that is the ratio of average signal power to the average noise power, we can calculate SQNR is equals to P average divided by quantization noise power is equals to P average divided by del square by 12, or 12 into P average divided by del square, or after putting this value, this relation of quantization noise error, we can also mention SQNR will be equals to 3L square P average divided by M square P, where MP is the peak power of the amplitude of the analog signal. Okay. Now, how we can exactly calculate this value? It will depend what kind of information or what kind of input signal we are using. For example, if we are using sinusoidal signal with the peak value of MP, then the P average will become M square of T. Okay. So, with the help of this SQNR, with the help of this relation 3L square P average divided by M square P, what our equation will become 3 into L square. L is equals to 2 raised to the power n. P average is M square of T divided by M square of P. That will be equals to 3 into 2 raised to the power 2n sigma square P divided by M square P. That will indicate the average power of the signal, that is sinusoidal in our case. So, it will become M square P by 2, the average power of the sinusoidal signal. So, the signal to quantization noise ratio will become 3 by 2, 2 raised to the power 2n. Simplifying this value in terms of dB, we will get SQNR in terms of dB 6.02n plus 1.761 times of dB, where n is the number of bits. Okay. There is one more thing which is called 6 dB rule. What is 6 dB rule in case of SQNR? If we want to calculate the SQNR, that is the general formula for this 3L square P average divided by M square P. P average will depend upon the type of information we are using as an input signal. So, converting the previous one in terms of dB, what we will get? We will get this value, that is 6.02n plus 10 log base 10 3 sigma square m divided by sigma square q times of dB. It is an important result. It states that for any arbitrary message signal, each additional bit, n is the number of bit. So each additional bit in the analog to digital conversion process, it increases the SQNR by 6 dB. If there will be an increment of 1 bit in ADC process, then what amount of signal to quantization noise ratio will increase? Approximately 6 times. This is called 6 dB rule. Okay, and this portion will depend. This in general we can represent with a constant alpha, and the value of this alpha will depend upon the type of signal we are using as an input signal. In case of binary PCM, we are using sinusoidal signal as an input signal, then the SQNR will come out 6.02n plus 1.761 times of dB. Okay, so this is the noise consideration in case of PCM system. So in this video lecture, we have discussed about the pulse code modulation system, what is PCM, the PCM transmission and reception system, the quantization process, the type of quantizations, and the noise consideration in PCM system. So this is all about this video lecture. Thank you everyone.